probably many of you did take, maybe gave courses on algebraic geometry, and the standard approach nowadays is the scheme theoretic, of course, and when one regards the spectrum of or even of an affine variety, one takes the prime spectrum, and points are not only maximal ideals, but also prime ideals. Points are not necessarily closed. When we study the algebraic group as a fine algebra involved, which actually I don't think I used the term of algebra, which is what with the group structure, the extra structure that the group gives on the space gives them. If you have a space, functions on it forms an algebra, so you have a product. But if you have a product on the space, then it gives a co-product on the level of functions, and together it called the structure that we get together is called usually Hopf algebra. And but if you take a fine algebra associated with a group, and you take the prime ideals, the space of prime ideals, then you don't see the group structure. It's only the closed point that you can multiply. So somehow since in any case over a field it doesn't make so much of a difference, it facilitates the approach to group theory if we discuss only maximal ideals as points in our spaces. Yeah, but this is not a tragic or dramatic difference between the theories. But in any case, so somehow we have so classical varieties are better than schemes. But on the other hand, if we just look at affine varieties, these are not enough. We need more general beasts because say even if we take, I don't know, the parabolic, take SL2R, SL2C, modulo that group is already P1C. This is not an affine variety. We need, if we want to study coset spaces even, we want our groups to act on things naturally, then we are already led to study things which are more general than just affine varieties. So now, in this hour, I guess, I want to discuss generalization of affine varieties into more general varieties. And so this is the subject of our study, and the approach to do this is some gluing procedure, the way one defines manifolds. And the main technical gadget that one uses is the object called sheaf. Sheaves of functions, hopefully. So before introducing it, so this is some device that helps us glue together things, and I hope this is familiar to most of you. Let me give an example outside of the theory of algebraic geometry, just to familiarize this object to begin with. Take X topological space. Say compact metrizable. Something you are happy with. One can, for every U in X open, one can associate the space C of U, and this is continuous functions. Say C star, say C value. Continuous functions on U. every continuous function on x restricts a continuous function on u, but maybe this is richer than, I mean, maybe we get more functions in a sense. On CU, for example, if we had, if x was R, local compact, something to make sense. If this is R, I can take on U, which is everything but, I can take 1 over x on R minus Z. This cannot be extended, of course. I didn't ask my functions to be bounded or completely supported or C0 or anything. And now one observes that you have natural maps. If U is, if V is in U, then there is a map from CU to C of V, which is just restriction. Of course, we have many theorems saying, I don't know, Pete's theorem that says that such maps are. Oh, okay, never mind. This guy here is a functor. If I think about this kind, if I think about inclusion as an arrow in the category of open sets on X, of X. Okay, so obviously when I have another guy here, W, I'm getting another restriction here, and the composition of these inclusions gives the composition of restrictions here, etc. Further, functions are local in nature. Somehow, in order to know a function, just need to know it at every point. So if I know a function on a covering of the space X, then I know it as a global object. Let me express this. If UI is a cover of X, and Fi, a function in CUI, and if I can glue them together, and here's the obstruction of gluing together. Whenever a function is defined on two domains, for every ij, fi restricted to uj, or to the common domain, u restricted to uj, equals fj intersect. Then I can glue the f's, if you wish. This is an exercise to you. Glue them, the fi's, into a global object, a global function. F, which is defined on X, such that fi is just f restricted to ui. And maybe just to make it more general and excuse me for doing so, this applies for the full space X, but also for any subspace of the full space X. So I can change this to be U here. So if UI is of U now. So one expresses this as the sheaf X. People like this shortened notation that I'm about to introduce. If you have functions on mu, Cu, think of C as a functor, as this functor. And so I can restrict the function from u to the various ui, and I'm getting a bunch of function spaces whenever I have a cover ui of u, and from these you have two natural arrows, these two, into the product over I and j of all the CUI in the set j. And what is written here, maybe, I mean, encoded in a phrase that this thing is exact. I mean, the term exact here just says that, basically. And this is the sheaf example. That then, so maybe.
What does double arrow mean?
Two arrows. We have two maps. The map to take the family Fi to the intersection with Ui. I mean, an element here
It's a tuple of functions.
is a tuple of functions, and you have two ways to restrict each function into this double product.
What are those two ways? Oh, I see.
Oh, maybe let me not remark too much about this. This is a graphic way to encode that axiom over here. So this is just a way of thinking. There is no much importance of this specific sequence here. This is just a way people memorize things. To me. So, given topological space X, we denote by top X the category of open sets. On X, a redshift is a functor defined on that category, such as this one. Functor into what? Then we will say this is a sheaf of C algebras, in our case. Sheaf of abelian groups, sheaf of sets, etc., etc., etc. And a plane-sheaf is called a sheaf if it satisfies the sheaf axiom. Somehow, so the sheaf axiom is something to say that our object could be thought of as functions on the space. And I don't want to, again, to dive into the general theory of sheaves. I don't think it's interesting for us right now. This would be a waste of our time here. Of course, one should study this, and, but somehow if u or x is glued out of pieces ui which I understand better, a sheaf is a way for us to understand how the global space is made out of these pieces. And this is exactly what we want when we study more general varieties and just define those. This is why I introduced this. And so now when I want, or maybe I should make one remark, that somehow in the study of topological spaces, classical topological spaces and continuous functions on them, this is really not needed. Somehow because we have splitting of unity techniques, etc., the global, every local function can be made global. The passage from global to local is not so dramatic as if you study polynomials or analytic functions. When you really have more functions on small pieces than on the full space. For example, on this projective variety, we don't have any, I didn't define yet, but still, we don't have any regular functions which is not constant. But on affine pieces of it, we have many. When we study more naive objects, we don't need this axiomatic approach, this gadget, but it is useful. So this is just an introduction. I didn't try to be too formal. Now when I want to introduce varieties, first I should understand what is a sheaf of functions on a usual affine variety. Those objects that I do understand. I want to understand those in sheaf theoretic manners. And I could do this in a more abstract way than the one I choose to express here. What I will express in a minute is a sheaf of regular functions, not only a general affine variety, but on an irreducible one. This facilitates the presentation, and I will explain why. So let me start by definition. Topological space. So we touched on that. I will be very brief here. A topological space is irreducible. The X. If whenever, for every closed set x1, x2, such that X is the union, either x1 is a full thing or x2 is a full thing. I cannot present it as a union of two spaces. If you didn't study algebraic geometry, you never saw this definition because exercise X Hausdorff and irreducible for Hausdorff spaces. They are irreducible if and only if they are just points. So this is not an interesting property. But for our spaces, for the heuristic topology, this is interesting. Exercise. And then third, space. So the topological space with term, and bear in mind if every collection of closed set at the minimum is a finite union of irreducible by geometry, this space, for example, is irreducible. The union of these two spaces is not. But it could be break down into two pieces, obviously. So this is how to prove this very, very briefly. Assume your space is not irreducible. Look at all closed subsets of your space. Sorry, assume your space is not such. It cannot be presented as a finite union of irreducible pieces. Look at all closed subsets of your space and ask which is the minimal one with this bad property. It cannot be represented as a finite union of closed irreducible subspaces. And find such. And the minimal guy that you find is obviously not irreducible. So it could be represented as a union of two things, but each of them is not that bad anymore. x1 and x2 each could be represented as a finite union of irreducible closed subspaces, so x is as well. Okay, so this very brief. Another exercise. Or maybe the exercise. Irreducible, this is an obvious remark, always implies connected. Connectedness cannot be represented as a union of two disjoint closed sets. But usually it doesn't go the other way around. I think this is exercise. Check that for algebraic groups. Irreducible and connected are the same. And every algebraic group, I'm talking about the recent topology here, as connected or irreducible is the same component of the identity which is normal because it is canonical somehow if you conjugate it stays, which is normal and of finite units. Finite index because of that.
But unifying algebraic group is an affine variety, and affine variety is a dual category to the category of affine algebras, where you assume that they have no nilpotent elements.
Yes.
And if an affine algebra.
Okay, so let me explain what is going on with. Let me explain this.
That by algebraic varieties you can reduce.
No, I didn't say this. So let me follow an exercise. For an affine variety, let me please explain. For an affine variety, x is irreducible if and only if OX is a domain. It doesn't contain zero divisors. When, I mean, this should be an example, maybe better example, easier variety drawn here. This is x, y equals z. So x, oh, maybe over xy minus 1. Yeah, here generates that. This is the dual object of that. Just xy. Sorry, just xy. The element x and the element y here are zero divisors. And somehow they are responsible to these two pieces. And the lack of zero divisors is exactly what makes a variety irreducible. And then this is a very standard and very easy exercise. So in my discussion, so since we can reduce to this, and since this really will facilitate my discussion in this, let me reduce this case. In our discussion, from now on, we assume most of the time that spaces of it are irreducible. Again, this is not truly necessary. It will be easier for me to explain things, because then I will deal with sheaf of regular functions which will not be some abstract object that I derived out of a sheafification of some presheaf, some bizarre procedure. I will have actual functions in the space. Because OX now is sometimes denoted KX, and in any case it is denoted the K algebra of regular functions on X is domain, hence has a field of fractions. Denoted now Kx that we think of as rational functions on X. Maybe I should add partially defined. One over X over there is not always defined. It is defined with a piece. It is a rational function. And they are not defined when the denominator is zero, which is a subvariate, a closed subvariate. So let me make a definition and a remark. If X is irreducible, X, a point in X, we define all sub little x to be all functions f over g in Kx, which are defined at little x, such that Gx is not zero. Or to be precise, this is a representative all functions, all elements, let me read it in a more formal way than written. All elements of Kx that could be represented as f mod g, where g is not 0 at little x. And let me make a remark now, that I can define this object for any variety, but I will then define it as some limiting process, as germs or function defined at the neighborhood of little x. So it will be a limit of some rings. And it is easier for me to just express it as space of functions, as a sub ring of this field. This is why I chosen to take an irreducible variety x. So everything that I will discuss is happening in some specified universe. Okay? So again, so this is an apology. Here's the theorem. So again, we may think of these as functions which are defined in neighborhoods of little x. Which neighborhood these functions are defined in? The open set in which g does not get 0. Or maybe actually in a slightly bigger neighborhood, because maybe I can represent the same function as f prime times g prime, and then it is also defined in a domain in which g prime does not get 0. Same function. Here's the theorem. Ox. Again, this is a subring of this one. And it is certainly contained in those elements are certainly defined at every point. There is an obvious containment, but this is actually an equation. This x I find irreducible. Proving the other equation. So I'm taking h. So this is, I want to think of it as some global function, a function that is defined everywhere. And I want to conclude that h is actually regular functions. Now, for every x in x, I can represent h as fx over gx with these guys, regular function, and gx at x is not 0. This statement is exactly that statement. Define I to be the ideal generated by all these gx's. Assume for a minute I claim that I is everything. So I look, maybe, claim. I'm claiming that. Assume not. If not, then I can find I can find some maximal ideal that contains I. And let me, of course, I think in algebra I denote ideal by M. When I think in geometry I denote ideal by X, but these are the same thing, right? So let me use the notation M sub X. We know the correspondence between maximal ideal points. For some maximal ideal corresponding to a point x. But this is exactly saying that there exists x, this precise little x, such that for every g in I, gx is 0. G is in that n, which is a contradiction. Why? Because G sub x0 is there. Right? The specific G sub x0 cannot satisfy this. Okay. So from this, maybe I'm starting from this. From this, I get that 1 is in I. And this means that I can represent 1 as some linear combination of elements in I. With clear notation, this would be some finite sum, Ti, Gi. Gi is in I. This is finite. Okay, what do we get by this? Now, what do? We start with this, taking this function h, and we want to show that this is regular, right? So let's present this. H as h times 1, or if you wish, as h times this sigma Ti, Gi, and 15. Ti h times Gi. The Gi's are Gx's, so maybe I should just use the term Gx sub I, G sub xi. Okay? These are the Gi's, and they correspond to some Fi's. This is some Ti, Fi, and Di. Okay, so now, having done this, I want to define the factor O, the sheaf O. We define the factor O from the topology of X to K algebras by U goes to OU. U is an open set in X, which I'm now defining to be all functions which are defined at that magnitude. And somehow, so this is exactly, these are the rational functions which are regular at U. This is the way to think of those things. And since we do think of Kx, that space over here, as space of functions, maybe not globally defined, this is an exercise to check that this is a sheaf. All forms a sheaf. And again, if I didn't choose X to be irreducible, then my checking here would be slightly more complicated. I should add some more words, which I don't want to do, but this could be done. So it helps me very much that all my functions are contained now in this universal object kx, k parenthesis x. Okay, and maybe I should have defined. Shall I leave it for the break for you to define what are maps, continuous maps between spaces with shifts on them. I will describe it in a minute, but I will not be super formal here. So if you have x to y, a map phi, and if you have u in here, then I have the open set phi minus 1 u here, and I'll have the space u or uy, oyu here, and I will have the space ox phi inverse u here, and I would want to have some phi star here, right? Or phi star sub u here. I want regular functions to be put into regular functions, and I want some compatibility condition here, some square diagram to be commutative whenever I have u and v. If you think of it, you get into the definition of a natural transformation between functors. I have a functor here, the sheaf of functions here is a functor, the sheaf of functions here is a functor, and I want this phi to be accompanied with this natural transformation. Assigned with every u, I want this v upper star sub u from this to that. And so I leave it for you to formulate it or to read it elsewhere exactly what definition is, though, even though I think I said it quite precisely, and check now for morphism. A morphism of a fine variety defined up the same way we have done of a fine variety gives morphisms of the spaces with sheaves, sometimes called in that concept ring spaces. It's shift, well, with shift of rings, right? Shifts of k algebras. So we get shifts of rings. Actually, already in the level of, if you take u to be y itself, then phi inverse u is x itself. We get the map between ox, oy to ox, which is everything. I mean, it should follow from this lemma, from this theorem, that this is the case. So actually, this for affine varieties, this is just a very, very complicated way to form the same object, because those ring spaces are just an equivalence of category. It's a very complicated way to describe morphisms, but it is local. Hence could be extended to things which are global things which are locally built out of affine varieties, and I will explain this after the break.